Okay, so we are going to pick up the discussion from what we were talking about before the test. Is this the idea of roadway design, designing of the vertical curves? And then the way we looked at it is, one way that we looked at it was, we are going to define the parabolic equation like this and be able to solve problems to find out at what stationing, what the elevation of the vertical curve is going to be. And that's a very important factor in design, because that's what you need to provide. At station, what should be the elevation so that the people who are building the roads can ultimately go and build that road at that elevation. Now, sometimes, and we solved a couple of problems there. One of the problems was that, we want to have, at a specific point, we want to have a certain elevation, right? So that's what we had there. And then when we solve that problem, we applied the parabolic equation that I showed you in the previous slide, y equal to ax squared plus bx plus c. And we used the property of the parabola, like the slope at the initial tangent or the slope of the slope at a given point, and property that it's an equal tangent to solve this problem. Now, what I want to do is I want to give you another perspective on how you might be able to define the equation of a parabolic curve. Okay. And in this case, we're going to define a different variable y. Okay. And that equation is called the offset form of the equation. Okay. The offset form of the equation. And this is what that offset form of the equation looks like. The offset form is y equal to capital A now, capital A divided by 2L times x squared. Now, here the terms mean slightly different things, right? Here the terms of this equation are not the same. Remember, in the original equation, y equal to ax squared plus bx plus c, y was the elevation of any given point, okay? In this case now, y is defined as the offset between initial tangent and the point on the curve. Okay, so y is not the elevation of this point. So y in this case is not the elevation of this point. But what it is, it's the difference in elevation between the initial tangent. It's the difference in elevation between the initial tangent here and the point on the curve. So it's this vertical distance right here. Okay, it's this distance I'm talking about. That's what offset is. Now, I have seen students make mistake in thinking about the offset equation, in that sometimes when they're talking about a point beyond the PVI, right? They think that, if I'm looking for the offset, this is going to be my offset. If I'm looking at point here and I want to find the offset at this point, let's say if I want to find the offset at this point, my offset is going to be right here. No, that would be incorrect, because offset is always defined from the initial tangent. So offset is always going to be defined relative to this tangent. And so that offset value is always going to be from the initial tangent. And this is what the offset is going to be at this point. Okay, so offset at PVI is going to be this right here. Okay, so the offset you can see. So one property of the offset that you can see from these figures is that the offset always increases, right? You can see that the distance between as the distance from PVC increases, the offset always goes up, right? And that's what you can see in this equation right here as well, right? You can see that this is like a monotonically increasing function because it's y. And remember, this y is now offset. It's not so in this equation, it's offset and not elevation, okay? So in the previous form of the equation that we did, y used to be elevation, but now we are defining y as the offset from the curve. Now this offset, why do we want to learn this? Because it can make solving some of the problems much easier than it used to be. Now, but let's quickly talk about all the other variables here as well. So why is the offset at any distance x? Now, x is the same way. So the way we measure the distance x, it's measured exactly the same way. Okay. Capital A is the absolute value of difference in grades. Okay. And then we measure this in feet per feet. Okay. So the unit of capital A here is feet per feet. It's the difference in the two grades. So if let's say this was 4% plus 4% and this was negative 3%, the capital A value will be 7% or 0.07. Okay, so it's the difference between the absolute value of the difference between the two grades. That's what we are talking about. Okay, so that's going to be feet per feet. And then x is exactly the same that it used to be in the previous equation. So this x value, so x is the same as the parabola equation, right? So whatever we had in the parabolic curve equation, we use the same definition of x. Okay. Now this offset can make life a little bit easier for you when you're trying to solve some problems. So remember this equation. So let me write down this equation over here. And let's see. Let's throw that equation on this side here. Y equal to capital A x squared, right? Divided by 2 times L. Okay? So that's my equation. So it's A times x squared. And I can probably draw a small x. It doesn't matter. So A times x squared divided by 2L. So remember this equation as we are solving any of these problems. Let's see. Let's take a look at the next slide. You can define some special values of the offset. If you plug in x equal to L over 2, that will define the offset at PVI, also called YM, Y sub M. And that was going to be AL over 8. I hope I don't have to explain how it came to be. That's like right here. Y equal to AX squared over 2L. You just plug in x equal to L divided by 2, L over 2. So if you plug in x equal to L over 2, which is right here, you're going to get, if you plug in x equal to L over 2, you're going to get YM equal to AL over 8. If you plug in x equal to L, you're going to get YF, the final offset. That's going to be just AL divided by 2. Okay, so these are some special cases of the offset value. Okay, so now let's look at, right? So we got this. Let's look at this example and think about how the offset can help us solve this problem. Okay, how offset can help us solve this problem. Now, the way the offsets work is that they can help you in making your calculations much easier. I want to solve this problem with the offset method, and then we can probably go back to the old problem that we did, also quickly discuss that problem with the offset method as well, and how this can be pretty easy to solve. So let's look at this. There is a vertical curve crosses a 4 feet diameter pipe. Okay, a 4 feet diameter pipe at right angles, right? So you designed a roadway. It has a vertical curve, and it crosses a pipe that has a 4 feet diameter. The pipe is located at station 110 plus 85, and its center line is at elevation 1091.60. So what's happening here is there is a pipe located somewhere, right? And think about the pipe as something that goes into the plane of the board. And then you have the center line of the pipe, right? So pipe is like this, right? The pipe goes into the plane of the board like this, and then this is the center line of the pipe. And they're telling you that this is located at a certain elevation. And in this example, that elevation is 1091.60 feet. Okay, so the elevation of this point is 1091.60 feet. Then there is a vertical curve. PVI of the vertical curve is at station 110 plus 00. Okay, so PVI is given. Okay, and then the station of this point is given. It's 110 plus 85. So the station here is 110 plus 85. So if I'm thinking about the PVI point, would I draw it to the left of this point or to the right? What is the PVI station that is given to me? The PVI is at station what? 110 plus 0, 0, right? So it's full 110 station. This is located at 110 full stations and then 85 feet. Okay. So by convention, the way we draw things from left to right here. So then my PVI was going to be, my stationing of PVI is going to be somewhere over here. And then the elevation of the PVI is 198.4 feet. 1098.4 feet. So where would my PVI be located? It's going to be to the left of it because the station is lower than this, or station is smaller than this. And then where is this located in terms of the elevation? Above this point or lower this point? Lower than this point? The elevation of the PVI. So if I want to figure out where the PVI is located, it's going to be higher than this point or lower than this point? It's 1098.4. The elevation here is 1091.6. So that means it's going to be located higher, right? So higher and to the left. So if I want to locate the PVI, it's going to be somewhere here, right? So I'm going to make it a little bit higher than this point and to the left. Is everybody clear on why I'm drawing it this way? The PVI, for whatever vertical curve I'm going to draw, I haven't drawn it because they haven't given me the grades yet. They will. But I'm just basically working off of the information that's provided to me right here. Okay. So it's going to be to the left because the station is lower, and it's going to be a little bit higher. So I'm going to probably draw it like over here. Okay. 1098. The vertical curve is equal tangent. You know, we know that all vertical curves in this class are going to be like that. So we know it's 600 feet long and it's equal tangent. So that means wherever I draw the PVC, it's going to be 300 feet from PVI. Wherever I draw the PVT, it's going to also be 300 feet from the PVI. Okay, horizontal distance, right? So that's how we define the length. And now the grade is plus 1.0, 1.2, and then negative 1.08. So it's not a sharp curve. So it looks something like this. So the curve looks something like this, right? It's going to be something like this, 1.2%. And then the grade coming out of it would be something like 1. Of course, it's not drawn to scale or anything, so never mind that. So this is my PVI, and then this is 1.2%, and then this is 1.08%, and then this is negative, right? So this is what the curve looks like. The initial grade is plus 1.2%. The final grade is negative 1.08%. One thing I want to keep emphasizing, if you're looking at a vertical curve problem, this is the profile view that you're looking at. This is the profile view you're always looking at. You're looking at the profile of the roadway as it goes up. So the travel direction for cars to travel on this road will be like going this way and then kind of going downhill that way. Okay, so you're looking at the profile view. And then these are going to be connected by a vertical curve. What kind of a curve would that be? Is it going to be sag vertical curve or crest vertical curve? It's going to be a crest vertical curve, right? Because you're going from an upgrade to a downgrade. So it's a crest vertical curve. So let me draw this over here. Something like this. And then you could say that this is your PVT. This is your PVC. Does that make sense? Right. So you got the PVC. And then you know the distances as well, right? So again, the 600 feet is the given length here. So because the length is 600 feet, you know that this is going to be horizontal distance. This is going to be 600 feet. And then you're going to know that half of it is going to be between PVC to PVI, 300 feet. And then PVI to PVT would also be 300 feet. Okay. Let's see what else they want us to look at. They want you to, so this is all the given information that I had. Okay, and then we know the elevation of this is 1098.4. So this pipe a little bit smaller because the pipe shouldn't be 4 feet diameter pipe, shouldn't be that big. Right, so it's a 4 feet diameter pipe. So this is the center line. Okay, so this is your pipe right here, and then this is your PVI. You know some elevations. You know the elevation of PVI is also 1098.60, right? 1098.4 feet. So you know the elevation. Now the question is, using offsets, determine the depth below the surface of the curve to the top of the pipe. You want to determine the clearance between the top of the pipe to the surface of the curve. Okay, so you're trying to find surface of the curve to the top of the pipe. You want to find, so this is your surface of the curve, and this is this is the surface of the curve, right? And this is the top of the pipe. So you're trying to find this distance. Now, why finding this distance might be useful is because you want to figure out how much clearance you have, right? You want to figure out how much clearance you have. Now, I may have drawn it incorrectly here because, again, this might be lower than this. So I'll have to think about, have I drawn this correctly? Because this is only a 1.08% grade. So this pipe might actually be located much lower than this, right? So, and why I know that I made a mistake in drawing it, because if you think about it, this is 1098.4, right? And you're coming down with only a 1.08% grade. So even if you come down 300 feet, right? So if you come down 300 feet of horizontal distance, you're going to only come out about 3.24 feet down, right? So even this point, you can figure out the elevation of PVT. So the elevation of PVT in this problem is going to be what? The elevation of PVT is going to be 1098.4 plus negative 1.02 or 0.8 over 100 times 300. Does that make sense to everybody? How am I finding the elevation of PVI? Right? And that will be 1098.4 minus, if I did the math correct, it's going to be 324, 3.24. Okay? So you can see the elevation of this point is going to be only 1095.16. 1095.16. So the elevation here is 1095.16. That means definitely if something is at elevation 1091.60, it's going to be located below the surface of the curve. Does that make sense for everybody? Okay. So this drawing is not quite correct, right? So again, you know, you think you look at these things, you try to draw them out correctly, and you know sometimes your intuition will be right, sometimes you know you'll draw it mistakenly. So what I'm going to do here is, the problem is not this. The problem looks something like this, because so the pipe is actually located. The pipe is actually located. So I want to draw it correctly now. 85 feet, right? So I have 85 feet. I should draw it here somewhere. And it's going to be right here. That makes sense, right? So why, you know, how we are drawing this pipe, it should be located below the curve. Yes, it should be to the right of it. And it should be, the PVI definitely is going to be higher. So we were not wrong about that, but we were just wrong about how much higher it's going to be, right? So just remember that as you're drawing it. So, and now we know that this is stationing, the elevation here is 1091.60. And then the station here is 110 plus 85. And the station here is, okay. Does the diagram now make sense to you all? Right? We haven't talked about offset or anything like that yet. So in these types of problems, it's a good idea to kind of look at the problem statement, try to draw things out, and see what that looks like. Okay, so now the question is, using offset, determine the depth below the surface of the curve. If I had read the full problem, I probably would have known that this is below the surface of the curve, right? The pipe is, see, it says using offset, determine the depth below the surface of the curve. So So below the surface of the curve. So basically what they're looking for is how far below the surface of the curve is to the top of the pipe, right? So this is the distance they're looking at. Now, these types of distances, why they are so important? They are so important because they can help you when you're designing the curve. You are making sure that, whatever pavement subbase or whatever you need to provide underneath that, you don't want that to be interfering with the pipe. So you want to make sure, how far below is that pipe. So you need to always know where these other elements of the transportation infrastructure or drainage infrastructure are located. So in this case, you're trying to find, if you design this curve to join this 1.2 and 1.08% grade, how far below is this pipe located? Okay. And now we're going to use offset. So in offset equation, the most important thing for us is usually this right here, is this initial tangent. So extending that initial tangent is important because we are always going to determine our offset relative to that initial tangent. So offset at this point, if I want to define offset, this is the point of interest where the pipe is located, the stationing at which the pipe is located. So my offset of interest is going to be this right here. That makes sense? The distance between the vertical distance between the initial tangent and any point on the curve. And I'm interested in the point at the same stationing where my pipe is located. Okay. So now let's think about what this offset is going to be like. And then hopefully that'll make our life pretty easy in terms of being able to find that information. So in the exam problem, if you can give me the correct offset at the right point of interest, that would go a long way in terms of, maybe solving the problem. Even if you don't solve the problem, you get a lot of points on that problem. If you can determine the correct offset from the initial tangent to the point of interest. So now you just have to figure out what is your point of interest that you're interested in and estimate the correct offset. So that's kind of what I'm doing. And that's how I want you to approach these problems. Okay. So the offset equation, you can see it on the board. It's y equal to capital AX squared divided by 2L, right? So I determine the offset equation as y equal to capital AX squared divided by 2L. The equation is right here as well. You can see. So now all we need to do is figure out all these values for this particular point to get this offset value. Okay. So what is the capital value for capital A? Capital A, I told you, is the absolute difference between the grades that are connected by your curve, right? So in this case, capital A would be absolute value of 1.2 minus, and I'm going to divide both of these by 100. So it's the absolute value of 1.2 over 100 minus 1.08 over 100. So total change in grade, it's 2.28 over 100. Or you can say 2.28%, but because I want you to enter that in the formula is feet per feet, so that's my capital A. Next thing I want to figure out, L value. Is L given in the problem for me? The length of the curve. Do we know L in this problem? We do, right? 600 feet. It's given. I'm going to plug that in, 600 feet. That's good. Now I need to figure out what is the X value for the point of interest. What is the X value? Now remember, X in this equation is exactly the same the way we defined it in our parabolic equation. The Y is different. Y is offset now. So I'm trying to find that because that's my Y is going to be. But my X is exactly the same. So what will be the X value here? Can you figure out what is the X value for this point of interest for which I'm trying to determine the offset? 385 is exactly right because it's the horizontal distance from PVC. So we know that PVC to PVI is 300 feet. And then we know that this distance after the PVI is 85 feet because that was the difference in stationing 110 plus 00 and 110 plus 85. So we know that the horizontal distance between PVI and this point of interest is 85 feet. So my X value is going to be 385 feet. So can I now, so if I look at this, I have all the values. So if you can get your calculators out and give me the offset value, or give me the offset value y that's going to be estimated by this equation. And now remember, what you're going to get is this distance. It's the offset between the initial tangent and the curve. Okay? So get me that value of y using your calculators, please. Okay, so the offset value, if you calculate it using the formula of like A, X, and L, if you plug in L value, X value, and A value, you're going to get 2.82 as your offset value. Is that right? 2.82 feet? Okay, so that's good. So we now have figured out that this distance between initial tangent and this line is 2.82 feet. I want to find this value, right? So I need to get, so if I can somehow figure out the elevation of this point, I can subtract from it 2.82, the offset, and I'll know where I'm at here. And then I know the elevation? So I need to find the top of the pipe and the surface of the curve. So this is what I need to find. So I need to find the elevation of which 2 points. I'm going to mark those and see if that makes sense to you. So if I need to find, my final answer is going to be this right here, right? From the top of the pipe to the surface of the curve, right? So I need these two elevation, and then I can subtract those, and I will get my answer, right? The clearance. So do we know the top of the pipe elevation? Do we know the elevation of the top of the pipe? We do, because we know the diameter of the pipe is 4 feet. So we know the radius of the pipe is going to be only 2 feet, right? So then the elevation of this point will be 1091.60 minus 2 feet, right? So it's going to be 1091.6 minus 2, and that's going to be 1089.6. Everybody good with that? Right? So I got the top of the pipe elevation to be 1089.6 feet, right? Because I subtracted the radius of the pipe. So center line elevation was 1091.6. I subtracted 2 feet from it. I got to the top of the pipe, which is going to be 1089.6. Yes.
Do they use the pipe to the center line to get the top of the pipe?
How about that? Thank you.
Yeah.
I would have posted this video and made a fool of myself, except I did it on purpose because I'm teaching a class and figuring out who's paying attention. So you add that 2 feet to get to the top of the pipe, right? Everybody good with that? How come you were good with the other thing too? You shouldn't have been. Okay, 1091.6 plus 2 feet, 1093.6 feet. Okay, so that's good. So I got 1 point. I need to figure out this point. I know the offset. All I need is, if I can somehow find the elevation of this point, I can get the elevation of this point by subtracting 2.82 feet. Now, how do I get the elevation of this point? That's pretty easy as well, because I know this is a point on the initial tangent whose slope I know is 1.2%. So if I know the elevation here, I can add that this is 85 feet, and I'm having a slope of 1.2%. So I can find the vertical elevation gain from here to here. So the elevation of this point would be, I can use the initial tangent. So I can use the elevation, use the initial tangent. So use initial tangent to get elevation of, so use the initial tangent to get the elevation of, use the initial tangent slope, right? So use the initial tangent slope to get elevation of point of interest on initial tangent, right? So now on the initial tangent, this is my point of interest. So basically all points that are located at that stationing 110 plus 85, because that's where all the action is, right? So I'm trying to find out what's going to be the elevation of the point of on the initial tangent at that station, right? So the point of interest is always 110 plus 85, right? Stationing 110 plus 85. So we're just figuring out what's going on at different elevation on this station, right? That's what my point of interest is. So now all you need to do is horizontal distance is 85. It's going to be, so I'm going to, PVI elevation is 1098.4 plus 1.2 over 100 times 85 feet horizontal distance. Does that make sense to everybody? What I'm doing here, I'm taking the elevation of PVI, I'm adding that slope, 1.2 over 100 plus 85. Okay, and so what do we get? You can use your calculators to find that value for me. What is that value?
1096.6.
1090.
Sorry, 29.42.
1090.42, because 42, I like 42 because that's going to make my numbers look good. So 1099.42 feet, right? So it's going to be a little bit higher, which makes sense. 1099.42, is that right? So 1098.4 plus 1.2% slope and 85 feet of horizontal distance between PVI. So basically, you're getting this number. You're getting this, and then you're going to reach here. And then once you know the elevation here, so now we can figure out the elevation to the top of the pipe. So now I can say, okay, the elevation to the top of the pipe, or top of the, or to the surface, elevation of the surface of the curve. And it's going to be just 1099.42 minus 2.8, right? So now this gets you 1099.42. This elevation is, we just figured out 1099.42. You subtract from it 2.82, and then you'll get what? You will get something 0.6. I knew that. 10, yeah, 1096.60. Okay. So then, are we ready to answer the question? Determine the depth below the surface of the curve to the top of the pipe. Are we ready to answer that question? Yeah, we are, because all we need is this. So we know both of these elevations. This is 1096.6. And then this is 1093.6 to the top of the pipe. So my answer is going to be, the clearance will be 1096.6 minus 1093.6. 3 feet is my answer of this problem, right? So it's going to be 3 feet is what's going to be. So the clearance will be the difference in elevation between this point and this point. So anytime you're talking about, estimating these clearances, which is a lot of times in roadway design, the offset equation can provide an alternative way. Sometimes like a little bit like again, you have to be careful about what distances you're calculating, but it can make your calculation life a little bit easier rather than estimating the 3 parameters of the vertical curve equation and so on and so forth. But ultimately, you're looking for the elevation of this point. You could have gotten it by, but the calculation on these were much simpler in terms of just kind of making sure that, we are aware of that approach. I'm going to not solve that problem, but I want to talk about it a little bit. If you go back to that example 2, you can also use that offset approach to determine, to design this curve, right? So you can easily find the length of the curve by using the offset approach. So this is going to be sort of a challenge for you. We solved this problem using the equation approach. Let's make sure that we can solve it using the offset approach as well. I'm not going to do that here. I want you to kind of take a look at it, and we'll talk about it at the beginning of the next class. So I want to give you another refresher for for the offset approach. So we'll talk about that. So you should be able to solve this problem using offset approach as well. Here you have to solve for L, the length. And again, that might make your problem rather easy because you know what's going to be the the elevation of PVI, and then you 200 feet with like a 2% grade. We want the 424.5 feet elevation. So you get the offset, and you just kind of take that offset equation ax squared over 2L and equate it to that offset value, and you will be able to solve for L rather easily. So think about that problem as we are. So yeah, that will be a good practice for you to solve this problem using offset method, because that will make the calculations much less messy than what we saw in the last class. So we'll talk about that very briefly in the next class, but you should be able to solve that by equating the offset to this equation and solving for L. Okay, we know the capital A value. We don't know the X value, but we can figure it out in terms of L, and then we have the 2L. So, all right. Okay, so next thing I want to talk about is this idea of horizontal curve, right? So now we are talking about not roadway changing its grades, like going upgrade or downgrade, going uphill and downhill like that. Now we are looking at roadways from the top. Okay, we're looking at it from the top, and this is the kind of the view that you see when you look at a Google map or Google Earth image, right? You're looking at it from the top, and all we're talking about is a change in direction of the roadway. Okay, so now let's think about, so now when we do these horizontal curve problems, the thing is that, I'm going to draw them, like when I draw these curves on the board, these horizontal curves on the board, they will pretty much look the same as my vertical curve, but I'm going to keep reminding you that I'm looking at the top view, okay? So I'm always looking at it from the top. So just remember that anytime I draw a horizontal curve like I'm drawing here, okay, these are looking at the roadway from the top. And now our job is not to change the grade, like upgrade or downgrade, but changing the direction at which the roadway travels. Now, the change in direction of a roadway can be achieved using what we call the low speed turns. That's when the roadway basically goes to an intersection and turns 90 degrees, right? So that will be your any intersection that you see. Sometimes you even see that, a roadway just kind of goes, you go, and then the roadway just turns direction like that. Maybe it's a T intersection or whatever. So in this scenario, you're achieving the change in direction by like having the cars all come all the way here and making a 90-degree turn. Now that happens sometimes. We have to do that some cases, right? And that happens all the time. But if you didn't have something like this, a T intersection, and you just wanted to basically, there was a hill or whatever there was, you're just trying to change this direction. Maybe there is a water body or whatever, and you're having people, you're trying to get people from here to here. In some cases, that change of direction has to be achieved using what we call the high-speed turns, and that is your horizontal curve, okay? So these horizontal curves are drawn like this, and in this case, these are circular curves, okay? So these arcs are circular curves. Again, if you look at the picture that's on your slides right here, what you will see at these are top views. They look very similar to how I was drawing the vertical curve, but they're completely different because now I'm actually looking at the horizontal plane from the top, okay? And then the roadways are changing direction from going this way to now going this other way. And then they have the same exact kind of things that we had before. Like they have, instead of PVC though, they have just PC. We call it point of curvature. We call it point of tangency, PT. So just we take out the V basically, right? And then PI is called the point of intersection. So it's very important for us to know that these are circular curves. So this is the circular curve that I'm talking about. This is the circular curve that I'm talking about, right? And then this circular curve is connecting these two tangents. And if you remember, and then if you draw out the radius for this curve and you kind of join that with the center, the radius is r for this curve. And if you recall the property of the circular arcs, what's the angle between a tangent and the radius drawn on the same point of the circle? What's the angle between those two? The angle between tangent and the radius. That anybody recall that from geometry? I know some of you might have taken it like 9th grade or something, but you remember? What's the angle? 90 degrees is exactly right. It's the 90-degree angle between the radius and the tangent. So we use that property a lot. So it may not look like it, but this angle is 90 degrees. Okay. And similarly, this angle is also 90 degrees. Okay. Then we define something. It's this angle of the circular curve. We call it delta, right? So that's the delta angle. And so if I ask you, what's this angle? So if this angle is delta over 2 and delta over 2, it's a symmetric situation here. So delta over 2 and delta over 2 is delta. What's going to be this angle right here? Anybody know? And I'm looking for that in terms of delta. 180 minus delta, right? That's exactly right, because you can see that these two angles are 90 degrees, right? So they add up to 180. And this is a quadrangle, right? So this has like 4 sides, a closed 4 sides shape. That means all of the angles have to add up to 360. Okay. And because these two add up to 180, all you're left with 180. So these two also has to add up to 180. And because this is delta, this angle is going to be 180 minus delta. Right? Makes sense, right? So, and then we're going to make use of this information. And the other thing is, like, if I were to extend this line, what's going to be this angle? Remember, this angle is now on a line, right? So this whole thing is on a line. So all of this has to add up to 180 as well. So that means this angle is going to be what? Delta, right? That's exactly right. So remember that, right? So if you sort of extend that initial tangent, now PC is the start of the point of the curve. Capital T is the tangent length right here. So this T is the tangent length. PI is the tangent intersection. It's the point of intersection. Delta is called the central angle of the curve. PT is called the ending point of the curve. So this is where the curve ends. And then we define it the same way. So PC will have a lower stationing than PT. Okay. So this is our convention when we draw the curves. PC will have a lower stationing and PT will have a higher stationing. And then M is the middle ordinate. E is the external distance. T is the tangent length. Now, the capital L here is interesting. It's not that interesting, but it's interesting because we just learned that in the vertical curve, we were measuring the straight line distance because we were projecting those points onto the horizontal curve, right? Now, the L, the length of the curve, it's going to be the length along this curve. It's not going to be capital C. Capital C is the chord length, which is different than the length of the curve. Now, in horizontal curves, this is the most important thing. The length of the curve is measured along the curve now. Why? Because the curve is located on the horizontal plane. Does that make sense? Right? Because we measure distances or length of the curves or length of the roadway alignment along horizontal plane. And now my horizontal plane or not my roadway along the horizontal plane is circular curve. So I need to measure the length of the curve itself. Okay. So remember that. So now length of the curve. So I'm just going to note here, it's going to be measured along. Okay. It's going to be measured along circular arc. That makes sense? Except for the spelling, measured for long circular arc. Now, since we're talking about the measure of length of a circular arc, what's the relationship that we use to measure the length of any circular arc? It's this relationship, okay? The relationship is the length, the arc length is equal to, the arc length is equal to radius multiplied by central angle. Okay? It's the radius multiplied by central angle. That's the arc length. Now, if you're talking about that arc length here, if you're trying to measure the arc length, one catch is about the unit of this angle, central angle. Okay, so if you're trying to apply this formula, arc length is equal to radius times the central angle. This central angle is measured in radians. It's measured in radians. Okay, not in degrees directly. Okay. Now, if again, recall that from your geometry, is that this idea of central angle being measured in radians. So how do we convert any angle that's measured in radians to measure them in degrees? Does anybody remember that? How do we convert an angle that's measured in radians if I want to measure them in degrees? What's the relationship? 1 multiplied by 180 over pi. That's great. Yeah, that's exactly what we need to do. So if you get an angle in radius, angle in degrees, if you want to find the angle in degrees, you kind of multiply this central angle in radians by 180 over pi. Okay, and then you can flip the operation, multiply any angles in degrees, and multiply that by pi over 180. Then you can get the angle in radian. So that's the other thing to remember, is that angle, so the arc length or the length of the curve is equal to radius times central angle, but measured in radian. Okay. So this is the other thing to remember. And then, once you know this, then you can, and then you can figure out 180 over pi is the conversion factor to go from radians to degrees. Pi over 180 is the conversion factor to go from degrees to radians. Okay, so that's the 180 over pi is your conversion factor. So angle in radians is equal to angle in degrees times pi over 180. Okay, so angle in radian is going to be angle in degrees . There is one more sort of measure of how we measure these curves. Is called the degree of curvature. So degree of curvature is the central angle that will be subtended by a curve exactly 100 feet of length. Okay, so exactly 100 feet of length. So D is the angle opposite to a 100 feet arc along the curve. So if you want to find the degree of curvature for any curve, it's going to be 5729.6 divided by R. Okay, 5729.6 divided by R. So your formula for degree of curvature D is 5729.6 divided by R. Now, if you're wondering where that came from, like such a specific number, because you're trying to figure out what's going to be the, so this is your degree of curvature, right? So this is your D. So degree of curvature, so the way we get that is because we know that the length of the full arc, if you go to full circle, the length of that circular arc is 2 times pi times R, right? And you know the angle that it would subtend on the central, at the center. What would be the angle subtended by an arc length 2 pi R at the center? If you think about the full circle, what would you think is the angle subtended, the central angle of a full circle? The central angle for a full circle. 360 degrees, right? So if I know that this 2 pi r is the arc length for full 360-degree angle, and if I want to find the degree of curvature d for a 100 feet arc, what would that look like? So this is the relationship 2 pi r over 360, 100 over d, right? It should be equal, right? Because if they're part of the same circle, I'm trying to find out what's the degree, the central angle subtended by a arc length of exactly 100 feet. So if you were to solve this, you will be finding that d will be equal to 5729.6 over r. And that's how we're doing it. So basically proportionality between a full circle and a 360-degree angle versus 100 feet arc length and d angle, which is the degree of curvature for any curve. So you can define it that way. Let's see what I have on the next slide. Okay, so these are some of the relationship. T is equal to r tangent delta over 2. I'm not going to go into the trigonometry of this, but I want you to think about this. Tangent is radius times tangent delta over 2. Chord length will be 2 times r sine delta over 2. So this is just basic trigonometry. E is the external coordinate. E is the external distance rather. M is the middle ordinate. M will be the full radius minus r cosine delta over 2. And then you can find all these. And then we talked about this a little bit here. L over, so if you take any length of the curve, L over 2 pi r equal to delta over 2 360. So if you know, and then if you want to find the length of any curve, it's going to be delta r over 57.3. And now in all of these formulas, you can plug in delta in degrees, right? So it's in all these formulas, you can put in the delta in degrees. So let me take out the eraser and then take this out. So here you can plug in these formulas, plug in delta in degrees. So let's see, there's a problem to be solved here. And we can come back to these formulas if needed. Okay, so let me erase all this. So this is the problem we want to solve. There is a horizontal curve is designed with a 2,000 feet radius. Okay. The curve has a tangent of 400 feet and the PI is at station 103 plus 0, 0. Okay. So let's try to draw this situation out. So we know that this is a circular curve that looks like this. Maybe I should draw a line here. Right? So this is my circular curve. And now I want to draw a curve that connects these two. And again, you're looking at it top view, right? So this is not vertical. This is not going up or down. This is not the profile view. This is the top view. So this is going to be my PC. So this is PC. This is PI. And this is PT. Right? So this is my PT right here. Right? This point is PT. Now the question is, I'm given the stationing of PI is 103 plus 0, 0, right? So this is the stationing, 103 plus 0, 0. Now the question is, how do I determine the stationing of PT? Now these stationing, you have to remember, this stationing is a little bit tricky when you're solving horizontal curve problems because the stationing is measured along alignments. Okay? This is measured along alignments. So the alignment that exists is the initial alignment that would have gone on like this. So if I were to sort of extend this line backwards, so this is my initial tangent. If that continued, this is where the alignment would have ended up with PI being 103 plus 0, 0. So if I want to find the stationing of PT, which is the problem is asking me for, stationing of PT, what I need to do is I cannot just add the tangents to PI and get the stationing of PT because there is no alignment on the horizontal plane that goes like this, at all. There's no such alignment that exists because the PI doesn't even exist, right? PI is the imaginary point where the two tangents would have met had there been no curve at all, right? So to actually get to PT, what I need to figure out is, I need to figure out the station of PC first, and then add to that the curve length, okay? So I need to figure out, I need to come back along this alignment. So I need to come back along this alignment this way, okay, to get the stationing of PC first, okay, and then add to that the length of the curve for this circular curve to get the stationing of PC. So what I will say is that the stationing of PC in this example, station of PC is equal to station of PI minus the tangent length. So I need to do is subtract this tangent length, and come back to the PC. Now, do I know the formula for tangent length? Yes, I do, because I know the tangent length is defined as R times tangent delta over 2. Right? R times tangent delta over 2. Now, the good news is that the curve has a tangent of 400 feet. So now the tangent is equal to 400 feet is already given to me. So I know that my tangent is 400 feet. Okay. So can you now tell me what is going to be the stationing of PC? So you basically subtract 400 feet from the stationing of PI. So then it will be 103 plus 00 minus 4 plus 00. So I'm going to put some parentheses here. So this is how you determine, and in this case, what would that look like? That will be just 99 plus 00. Okay, so what I'll do is, what I did was I subtracted the 4 full station from the PC. Yes?
Is the tangent plate the horizontal component, or is it that
Okay, so that's a good question. So they're all horizontal components, by the way, because you're looking at the top view, everything is happening on that same plane, right? But so when you're talking about so this is the tangent length. So if you think about what the tangent length looks like, it's this right here. It's this distance. This is 400 feet. It's this distance from here to here along this line, along the tangent. That's 400 feet. So to find the stationing of PC, you need to come back on this initial tangent alignment 400 feet. And that's what I did by subtracting the tangent length from it. Okay. Now, so you got the stationing of PC. That's good, right? So that's your one answer. But that's not what they're asking though, right? It's not the answer. Determine the stationing of PT is what they're after. So to go to stationing of PT, what you need to do is you need to get to the stationing of PC, which you just did. Stationing of PC is 99, right? So the station here is 99 plus 00. Now, to get to stationing of PT, what do you need to do? You need to add the length of the curve. Now, this is the tricky part. I've seen students make mistake. Is this they think about. So this is my stationing of PC. So this is right. So stationing of PC is 99 plus 00. Now to get the stationing of PT, you find out station of PC, which we just did. You add to that the curve length, okay, or length of the curve. But this is the tricky part. Now the length of the curve is the actual circular length, circular arc length. Okay. Now, do I have enough information here to find the arc length? We know that the arc length is angle times the radius, right? If the angle is measured in radius. We know the radius is 2000 feet, but do we know the central angle in this problem? Do we know the central angle? Not yet, right? That's the growth mindset, right? Not yet. We'll figure out that central angle, but we don't know it yet. We can find the central angle by knowing that my tangent length is equal to r times tangent delta over 2. So that means tangent 400 is equal to 2000 feet radius times tan, right? So I can solve this equation, this trigonometric equation, because I know the tangent length is 400 feet, but I also know that the tangent length is r tangent delta over 2. So I can solve this trigonometric equation for delta, which will give me what? Delta equal to what? You can take out your calculators and tell me what delta is going to be for this equation, so that the tangent length is exactly 400. You know, if you have the value here. 22.63. Right? Perfect. So this is great. But this is in degrees though. Right? So remember that the units that will come out of this is going to be degrees. If your calculator is set that way, you can also use your calculator to convert any angle into degrees to radians. But then we also have an easier conversion by doing pi over 180. Now, why am I talking about this? Because the arc length that I need to find is, it's going to be 2000 feet radius times the angle 22.63. But I can't just do that directly, because that would not give me the correct arc length, because I'm inputting my angle in degree, right? So what I need to do is I need to put this angle into radians to be able to get that. And that would come from by multiplying this by pi over 180. Okay. So my arc length is going to be 2000 times 22.63, the central angle. And then make sure that this is delta, right? Not delta over 2. And then pi over 180. And then my arc length, what is that going to give me? Does anybody have the value? 767 feet. So that means I have like 7 full station worth of curve and then 67 additional feet. Okay. So then, is that correct? Everybody on board with this number? 790? Okay. I'm clueless. So let's go with 790. Okay. The 2000, the radius times the angle. So radius times the angle, but measured in radians. And then you got 790 feet. Let's just go with that. Okay. So then you have the 7 full stations. So then you can come back to this equation. The station of PT is station of PC, which is 99 plus 00, which you just determined, plus 790 feet. And that will give me 106 plus 00, or plus 90, right? So 99 plus 7 full station is 106, and then 90 additional feet used to be the station of PT. It's going to be 106 plus 90. Okay. So now to think about this, like, so the key difference between horizontal and vertical curves, the way we are solving the problems, is that now we have to measure the actual length of the curve. Okay. Make use of that angle times radius information, and then solve problem that way. And now the thing about this is that, to remember, and I'm going to stop in just a second here, is that you can find, like, if you think about any point on this curve, you can find the equation of any, you can find the stationing of any point on the curve by doing, by finding just the length up to that point. Actually, there is a homework problem that you'll be solving where you're going to have to find the stationing of the point somewhere in the middle right here. Okay. So then what you'll need to do is you need to find what the angle is. What is just this angle subtended up to this point? Then you can find the arc length only up to this point. Okay. So remember that you might have to solve problems like that. Okay. So any point on the curve, it could be here, could be here. I mean, if you're going full curve, then you're going all the way to PT, but just make sure that you can do that. All right. I will see you all on Thursday. We'll have a guest speaker on Thursday for about 35, 40 minutes. We're going to talk about some real world applications of what we are learning. And then we're going to continue this discussion. Thank you so much.
I didn't get my.
Yeah. And yeah, if you haven't collected the exam, you can get them here. Thank you.